4.6 Related Rates. So in this section we're going to be talking about relating two variables together with usually respect to time. So in example 1 we're going to talk about how to derive formulas using implicit differentiation in terms of volume or area. So we want to assume that the radius of a sphere is a differentiable function of t and let v be the volume of the sphere. Find an equation that relates dv dt and dr dt. So what this means, this right here is the rate that the volume changes over time, and this is the rate that the radius changes over time. So what we have here is we want to know as the radius gets bigger or smaller, so will the volume. This is because if you have a sphere and the radius gets smaller, so does the volume. So we want to know how fast the volume is changing. So the first thing we're going to need is a formula for volume. We know that volume of a sphere is 4/3 pi r cubed. So what we need to do now is take the derivative of that with respect to t. So d dt and d dt. This is very similar to implicit differentiation, except this time we're introducing a new variable, which is t. So on the left, we're going to get dv dt is equal to 4/3 and pi are a constant, so you get 4/3 pi. The derivative of r cubed is going to be 3r squared times the derivative of r, dr dt. This is r prime. So this is the implicit differentiation. So then we do a little simplifying and we get dv dt is equal to 4 pi r squared dr dt. That's it. Because now we can relate the change in the volume to the change in the radius. So if you're given the change in the radius and the radius, you can find the change in volume, or if you have the change in the volume and the radius, you can find the change in the radius at that time, and so on. Alright, part B. Assume the radius r and height h of a cone are differentiable functions, and let v be the volume of the cone. Find the equation that relates dv dt, dr dt, and dh dt. So the first thing you need to know is the volume of a cone, and the volume of a cone is 1/3 pi r squared h. Okay, that's because if we have a cone, it looks something like this. And so here is r, here is h. So what I want you to do right now is try to take the derivative on your own. See if you can figure it out. Take a second, pause the video, and then unpause it when you're ready. Alright, here we go. So we get that dv dt is equal to 1/3 pi. Those are constants, so they stay on the outside. Then, if you notice, I have two different variables here. That means I have to use the product rule because they're being multiplied. So I get 2r dr dt, because the derivative of r squared with respect to t, you have to use the chain rule and implicit differentiation. And then the h comes down, plus r squared. The derivative of h is 1, And then using implicit differentiation, you get dH dt. Now in the last example, I want you to try to find the volume of a right cylinder. And I want you to derive the volume if R and H are differentiable functions. So go ahead right now, pause the video, and try that out. Alright, let's see if we did it. So volume is equal to pi r squared h. If you didn't know that, that's because here's the cylinder. So the volume is the area of the top piece, which is pi r squared, times the height. So we take the derivative, and we get dv dt is equal to pi. Right here you have to use the product rule because you have a multiplication of two variables. So you get 2r dr dt times h plus r squared dh dt. We're going to do a little bit simplifying, and we get dv dt is equal to pi 2rh dr dt plus r squared dh dt, and that's it.